Pythagorean theorem, as everybody knew before they started the semester, is the theorem that relates together the three lengths of the sides of a right triangle. And so we begin with a triangle ABC, and the statement of the theorem labels it in such a way that they're calling the length of the hypotenuse small lowercase c, and then A and B are the lengths of the two non-hypotenuse sides, so we have a right angle right here. And of course, the famous equation which defines the theorem is that the sum of the squares of the legs, a squared plus b squared, is equal to the square of the length of the hypotenuse, which is c. And so, again, the author has been not particularly careful in defining his vertices, capital A, capital B, capital C, but it's clear from the context as the proof begins that he defines it in such a way that the vertex at capital C is intended to be our right angle, right? So that the side opposite that vertex is the side that we call the hypotenuse. So the overall gist of the proof seems to be that the author sets up this triangle, drops an altitude, interestingly enough, from the vertex at C down to the hypotenuse. So not only did we start with a right triangle, but the author also creates two more right triangles in the process. And that seems like a strange thing to do until you find out that the reason for doing so is to create some opportunities for similarity. So we create an opportunity for one pair of similar triangles, CBD and ABC. So ABC is the big one, and also ACD and ABC. So by dropping that altitude, not only do we create one pair of similar triangles, but we actually create two pairs of similar triangles. And those pairs actually have one triangle in common, namely the big one, ABC. So by dropping this altitude to the hypotenuse, we have divided an original triangle into two triangles which are both similar to the original triangle, which is what we'll prove here. And since we have then three triangles, all of which are similar to one another, we have a whole bunch of different ratios that we know are all going to be equal by virtue of that similarity. And with enough equalities of ratios, we can do some algebra to move some things around and show that the Pythagorean theorem does in fact hold. The formula holds a squared plus b squared equals c squared. So let's take a look back. That's kind of the overall structure, the main idea of this proof. Let's take a look at what you all said in your annotations. So, first of all, how do we know, as the author asserts, that all of these different triangles that we said were similar just now, so this one and this one, CDB, and then also the big one, so all three of those triangles are all mutually similar one to another. So what you focused in on this, so Rachel's saying that, or Raquel rather, is saying that we'd like some more explanation on the AA similarity condition. And I would agree. I think if one of you had written this proof on a homework, for example, I'd probably let it slide on an exam. But if you wrote this on a homework, I would probably circle this and say, okay, you're using the similarity criterion, but which angles are you using to substantiate this comparison? Looking in this triangle, let's label some of the angles that we know that we know. What angles are we absolutely sure about to start things off? Give me one angle whose measure we absolutely know. CDA is a 90-degree angle. Likewise, CDB, 90-degree angle. Okay, so far so good. So now we have one pair of congruent. Maybe I'll make those congruence marks instead, because that's what's really at issue here. We have one pair of congruent angles right there. What's another? Can we find another pair of congruent angles in this? Because we only need one more pair in order to make the AA assertion. But the problem right now is that the two angles that we labeled belong respectively to the triangle ACD and to the triangle CBD, but neither of those angles belongs to our original triangle, ABC, and that's the rub, right? That's what seems to be the way the author is making this argument, is that we're trying to relate angles in these smaller triangles back to angles in the big original triangle in some way. So maybe another way to look at this would be to take some angle from my original triangle. Let's say I take this one right here, the angle CAD, and ask the question, to what angle in one of the smaller triangles is it congruent? Yeah, right, back to CAD itself. So the angle CAD, and this is going to look weird, but I'm just going to write it anyway, is congruent to the angle CAD. But we think of CAD, sorry, actually, why don't I write that as CAB? Yeah, thank you. That's what I wanted to do. That makes a little bit more sense. So CAB is an angle in our big original triangle. CAD is the same angle, just in our smaller triangle, the triangle ADC. So that gives me one angle that's in common to ABC as well as to ACD. So actually, I'm going to move this observation over to here instead, because we're really talking about these two triangles. And then maybe I'll also flip-flop the two sides here. So angle CAD and angle CAB are congruent. So that gives me one angle. So what's another?
We do similarly CBD and CBA.
CBD and CBA. So let me make that congruence here. CBD and CBA, and that would give me a congruent pair of angles in these two triangles. Okay. All right, we're making some progress. But again, those two angles belong to different pairs of triangles. So we still haven't landed a single AA argument yet. Yeah.
So from here, can you say because CDA and CDB are both right angles?
Okay.
And the triangle is 180 degrees. That each of the paired triangles is just missing from the other components.
Yeah. Okay.
Did you construct the big triangle to be a right triangle?
And that's right. That's, I think, the other piece of the puzzle. Right. So your comment is that CDA and CDB are both right angles. So in particular, those two angles are congruent to one another. But then your comment is, well, our original triangle, ABC, was a right triangle by assumption. Right? And so which angle in our original triangle is 90 degrees? ACB. And in fact, that's really important because now this gives us a link between the blue angle in the big triangle to both of the blue angles in our smaller triangles. And we can use that same observation in both cases. So what do we call that? ACB, which is the right angle in our big original triangle. So I'm going to say 90 degrees. And that is then congruent to, in our smaller triangle ACD, it's congruent to the angle ADC. ADC. And so there's our pair of angles that we can use for our AA criterion for for ACD, similar to ABC. And then that very same argument, using the right angle in our original big triangle, which exists by construction, that's congruent now to the right angle BDC in our other subtriangle, which gives us AA similarity for that pair of triangles. So that unpacks which angles are being used to assert AA similarity for each of these pairs. All that we really needed to make this AA argument was the congruence of these three angles. Why was it important that those angles were 90 degrees? 90 degrees was important because it's what allowed us to conclude that the blue angle on the left and the blue angle on the right were congruent to one another. Right? Because those angles were created by drawing the segment CD down to the hypotenuse, which is a straight line. Right? And so if I cut a straight line into two congruent angles, then those two congruent angles, those two opposite, well, they would be supplementary in this case, right? Which makes them, since they're equal, well, they're equal because they're 90 degrees. So we needed the 90 degrees in order to establish the congruence of those two angles, the blue angle on the left here and the blue angle on the right. But it's sort of interesting that we didn't need it to be 90 degrees in order to do AA, but we needed it to be 90 degrees in order to connect these two AA arguments together. so that what we end up with is a set of 3 mutually congruent angles, and so 3 mutually similar triangles. So now we can finish this proof, because we have 3 similar triangles. Every triangle we see in this figure is similar to every other triangle we see in this figure, right? Which is awesome. So that means that we get a whole bunch of different ratios that we all know are going to be the same. And if we wanted to, so the author just picks a couple of them, and one of the questions that came up in the annotation is, well, why did we pick these ones? Right? How did we choose A over Q and C over A and so forth? And I don't know that I have any better answer than any of you had for this. Because what I might do in this case, if I'm writing this proof for the first time and I don't know where to go with it, I might just list out every ratio that I know is equal to every other ratio and see what it gives me. So we have 3 similar triangles, and let's see if we can write the ratios for all of them. So we have ABC on the one hand, and we have a DC on the other, and then we also have BDC. And the sides of the triangle ABC are A, B, and C. The sides of the triangle ADC, let's make sure that we get the right correspondences here. The sides of this triangle, which correspond to it, we need this, the sides opposite angle A are going to correspond to one another, right? And so D is going to correspond in the small triangle to the side which is opposite the same angle in the bigger triangle, which is A. So A is going to correspond to D. B, which is opposite the right angle, so it's the hypotenuse in the smaller triangle, will correspond to the hypotenuse in the bigger triangle, and the hypotenuse in the bigger triangle is C. And then that leaves us with the last side that corresponds. P in the smaller triangle will correspond to C, because those are opposite the angle, which is neither the right angle nor the angle A. So there are our corresponding sides from this pair of similar triangles. Then we'll repeat the same thing with BDC. So in triangle BDC, the side opposite the angle at B is D, and in ABC, the side opposite the angle B is B. So B and D are going to correspond one to another. I'll put that over here. And then the hypotenuse of the big triangle, C, is going to correspond to the hypotenuse of the smaller triangle, which will be A in this case. And then the last side that we didn't label is Q. So here are all of our sets of corresponding sides in our triplet of similar triangles. And so now, any ratio that we might need to make, we can make just by dividing any 2 quantities from one of these rows will equal the quotient of any 2 quantities from one of those other rows. So here where the author picks A over Q, so that's picking A and Q from the first row down here. But then the author equates that to C over A, and where are those coming from? Yeah, those came from the third row, right? But that's the power here, is we can pick a lot of different ratios to set equal to one another here. So if I were the author of this proof, probably what I did is I probably am doing a little bit of working backwards, looking ahead. The only other relationship that we have between all these different variables is the fact that C, Q, and P are actually related one to another. That C, the length of the hypotenuse, is divided into 2 pieces by P and Q. And because this is a straight angle, because ADB is a straight angle, that means that AD plus DB is going to be equal to AB. Right? And so P plus Q is equal to C, which is, the author waits until right here to pull out that observation. But probably had it in his mind while writing this proof in the first place. So I think here's where we would go with this. I'm kind of, again, looking backwards. We want to prove something that has an a squared in it. And so what we'd like is a pair of ratios where a plays the numerator in one of them and the denominator in the other. Right? And likewise with the b squareds. We need a pair of ratios that are equal, in which b plays the numerator in one of them and the denominator in the other, so that that equality of ratios tells us something when we cross multiply about, respectively, a squared and b squared. And looking ahead, we would like for whatever it tells us to be something that when we add them together that we get c squared. And we know that when we add p and q together, we get c. So the strategic choice here is, first of all, we want the a's and the b's to be in ratios in which one of them is numerator, or in which it's a numerator of one and the denominator of the other. So that's the first thing that we wanted, because we wanted to get a squared and b squared into the puzzle. But then looking at the other parts of those ratios, we wanted those other parts to involve p's and q's, so that hopefully we can add those together and get a c. But that's only going to be useful for us if when we add them together we also have another factor of c that can account for the squaring that happens down here. So that might have been the behind the scenes into how this proof kind of... So for the record, it does matter how we write our similar triangles. So when we set up the correspondence of these sides, A, B, and C, we should preserve that correspondence in how we use the notation for similar triangles. And so ABC centers C, our right angle, as the last one of the vertices, and then A as the first one. So where I'd had ADC before, I still want A first, because that's the same corresponding angle, but I need my right angle to be last. So I want ACD in that case. ACD. And then likewise, I need my hypotenuse to come last, sorry, my right angle to come last in BDC as well. So, and the angle that is equal to A should come first. So I think what I want there is CBD. Yeah, that's something that every so often it crosses my mind when I'm writing up one of these proofs. Like, do I have the order of those vertices correct when you're making a congruence or a similarity assertion? And it really should matter. And thank you for policing me on that, because it's important to have that be as accurate as possible. So the proof concludes by the author just taking the left-hand side of the Pythagorean theorem and saying, what can I conclude about this? Now that I know all that I know about the relationships between A, B, C, P, D, and Q, what do all those relationships tell me specifically about A squared plus B squared? And because of the similarities that allowed us to conclude A squared is equal to CQ and B squared is equal to CP, we now know that when we add those two together, we get C times Q plus P. And because Q plus P is equal to C in turn, it proves that A squared plus B squared is C squared. Right? So it's often really helpful in writing a proof if you're sort of, if you feel like you've lost your way, go back to the original statement of the theorem and say, what am I really trying to prove here? Often you'll find yourself at the beginning of a proof kind of writing, we want to show that blank. Right? Just to remind yourself at the beginning. Well, you might have to remind yourself in the middle. You might have to remind yourself again at the end, too, right? But going back to that original statement and saying, do I have enough on my plate? Have I made enough of a case in order to return to our original statement and to prove it? At this point in the proof, the author did. So a quick addendum to this proof. Oh, gosh, now why am I having more trouble with this? Hold on. So I had C here, right?
Yeah.
Okay, so let's talk about that. So the length of the side C in ACD, isn't one of the sides, as you were saying. And so what belongs here? What corresponds to... Oh, wait, yeah, so that's actually, I think that's P, isn't it?
Yeah, and then P
That's
would be
P,
B.
and this would be B.
Yeah.
Okay, right, because, all right, so the last line are all of our hypotenuses, right? And so C, B, and A, that's what should be on the last line. Okay. So if you've made it to the end of this video, please go back in your notes and change this part of the table. Now, it turns out we didn't end up using those two in the original part of the argument made up here, but we would if we had looked at the ratio he set up on the right. So for your own sanity and for my ability to sleep better tonight, please change that in your notes if you've made it to the end of this video.